Let's take a look at the third case of graphing a function given another graph. This time we're going to go from the original f of x all the way to the second derivative. Here we have our original function. I've marked on it a lot already. You can see we're going to be using several things. Most notably will be concavity. We can see this graph changes concavity several times from concave up, concave down, then back to up and down again. Therefore, it's going to have some inflection points. We also see some points where the original graph doesn't have a tangent line. In that case, the second derivative cannot have a point there at all. It's going to be undefined there. So we can use some information about f of x to get a pretty good idea of what f double prime of x is. We're not going to get too in depth. I mean, if you really wanted to get very, very accurate, you would graph f prime first and then use f prime to graph f double prime. In other words, basically use the last two cases we studied. But a lot of times you just don't have time to do that. You just want a general look at what its second derivative is going to look like given the original. Following is the graph of f of x. Use the graph of f of x to sketch the graph of f double prime of x, the second derivative of f of x. So here it is. It goes from something that I'm not really sure. It's so steep it's hard to tell whether it's concave up or down. But at -6, it's pointy, so the derivative is not going to exist there. And the second derivative is definitely not going to exist. Concave up, concave down, concave up, down, and then probably up again, my guess would be. So we are going to use concavity to figure out things about the second derivative. So where is f of x concave up on this interval? Well, we're going to say from -6 to -3.8. So somewhere right past -4. Then from -0.5 to 3. And then from 5 to infinity. So let me ask you this. If f of x is concave up, what do you think is going to be true about the second derivative? I'll give you a second to think about it, and then I'll answer that question for you. Well, think about this. The derivative, so f prime, is going to be increasing, right? Well, if the derivative is increasing, that means its slopes are positive. So since its slopes are positive, f double prime is going to be positive. So whenever f of x is concave up, f double prime will be positive. It will be positive on these intervals we just determined for concavity. All right, in the same way, now remember what positive means. I'll go back and talk about that. On all of these intervals right here, f prime of x will be above the x-axis. All right, next, where is f of x concave down? We're going to say from -infinity to -6, it's concave down from -3.8 to -0.5, and then from 3 to 5. So, in the same way, since f of x is concave down there, the second derivative is going to be negative. So f prime of x will be below the x-axis on these intervals because f of x is concave down there. So whenever f of x is concave down, f double prime will be negative. Okay, step 5. Where does f of x have an inflection point with a defined tangent line? We learned from the last video that if the inflection point doesn't have a defined tangent line, i.e. vertical tangent line, then the derivative is not going to have a relative extrema. But here, at x equals -3.8, x equals -0.5, and x equals 3, we do have inflection points with defined tangent lines. What is that going to mean for the derivative? Well, it's going to be going from positive to negative or negative to positive. It's going to have x-intercepts. F prime of x will have x-intercepts at these following points because f of x has point of inflections there with defined tangent lines. Okay, step 7, where does f of x have undefined concavity? That's at -6 and 5, simply because the tangent line doesn't exist. Well, if it has undefined concavity, then f double prime of x is undefined there, since f double prime of x is largely the concavity of the original graph. So f double prime of x is undefined at x equals -6 and x equals 5 because the concavity of f of x is undefined there. Step 9, we're going to plot our points and asymptotes. Now, just so you know, the x-axis itself is actually right here. Okay, its actual values are down there. So just so we know, here's our line. We already know kind of where the graph is above and below the x-axis. Remember, it's going to start out, it's going to be negative from -infinity to -6. So when we go to connect these points, we know that our graph is going to be somewhere down here, right? And we have an asymptote here, so that's going to give us a pretty good idea of what the graph is going to look like. Okay. Now I should say, I said we have an asymptote here. The thing is, you know, it might be, it could possibly be a hole. We just know it doesn't exist there, so there's not going to be any points there. But since it was pointy there, it leads me to believe that it's actually going to be asymptote. And then after -6, we see that the graph is going to be positive from -6 to -3.8. So that means that up until about right here, we know the graph is going to be above the x-axis. Then again, we can see it's going to be negative again from -3.8 to -0.5. Then it'll become positive again from -0.5 to 3, and then back to negative from 3 to 5. So it's going to alternate back and forth from negative to positive and positive to negative. Last thing we're going to do is just connect the dots with that information. And again, our x-axis is actually right here. So we can see this graph goes. Now I didn't plot up until -6. We knew it was going to be negative there. My guess would be that it probably, well, if it's negative up until -6, you know, it's hard to say actually. Based on the original graph, we don't have a lot of information. We just know it's going to be down there, so it might look like that, but then again, there is no asymptote there. So I don't know actually what it's going to look like. I just know it's going to be negative. The middle is what we're going to focus on in this graph, since most of the graph that we were given from the original is in between -6 and 6. But we can see that, you know, the concavity, it's really concave down here, like extremely concave down, meaning the slopes of the tangent lines are really, really negative. So that leads me to believe that it's going to be really, really negative over here. Now it might be positive before that point, so another way you could think about it, since there's an asymptote there, you know, it might look something like this as well, but because it could be positive somewhere else to the left. But anyways, like I said, we're just going to focus on mainly from -6 to 6, or actually -6 to 5, which is where our asymptotes are. But we said it was above the x-axis from -6 to around -4. We said there was an x-intercept at -4, 0. Then it was below the x-axis from -4 to -0.5. Then from -0.5 back to 3, it's going to be above. And then after 3, it's going to be below. And there's asymptotes here, so we're going to sketch these, making sure to hug the asymptotes. We can draw arrows here. Now again, you might be thinking, okay, what's happening past our 5? Well, we said that past 5 is going to be positive again. So, you know, it will have to jump back up past 5. What does that graph look like? Well, it looks to me like there's probably going to be maybe another horizontal asymptote, maybe a horizontal asymptote for the second derivative, but that's really hard to find given the original. But we just know it's going to be somewhere up above the x-axis, so it could look something like this. It's hard to say. Again, there's not much information there, so I'm just going to focus on the middle of the graph. So there we have it. There's the graph of the second derivative given the original. The main focus is on the fact that the second derivative depends on the concavity of the original function. And it's going to have x-intercepts wherever the original has inflection points with defined tangent lines. It's going to be above the x-axis whenever the original is concave up, and below the x-axis wherever the original is concave down. All right, that's it for this particular example. Again, notice that the second derivative looks very little like the first derivative, and that just happens whenever we have graphs of functions. They change based on tangent lines and concavity. The shapes are naturally going to change. If you have any other questions about this example, let me know.